Good morning everyone. So here is my second lecture, which is based on Nyquist criteria for 0 ISI for the subject digital communication, and the code is KEC 601. So in the previous lecture we have discussed about the Nyquist criteria, and in this lecture we are going to discuss about what are the different factors by which we can combat our intersymbol interference. And there is the main criteria which is based on Nyquist. According to that criteria, we will see how we can easily cover up all these ISI problem in the your digital communication. So next we can see from the figure that what is intersymbol interference. So basically intersymbol interference occurs when a pulse spread out in such a way that it interferes with the adjacent pulses at the same sample instant. So basically what will happen, whenever the data is sending from a transmitter to receiver, it will be sent in the form of the pulses in the case of the digital communication. So the data pattern will be sent from the transmitter to receiver. As the digital pattern is transmitted, it will be overlapped among themselves, and which will create a problem for the communication. So whenever the pulses will be overlapping, obviously the data which we want at the receiver will not be the same as the transmitted data. So that problem is called as intersymbol interference. So whenever the pulse is spread in such a way that it interferes with the adjacent pulses at the sample instant, then it will create the problem that is called as intersymbol interference. So here there is a figure below which has an example of NRZ line code, which is non-return to 0 line code. So we can have a non-return to 0 line code. The channel outputs are shown as a spreaded width, that is TB becomes 2 TB. So what will happen, whatever the data 101011 pattern is sending, so this is the data which is sending from the transmitter, and for every data there is a pulse. So for every data there is some pulse. For 0 there is no pulse, for 1 there is a pulse, for 0 there is no pulse, again for 1 is pulse, and for 1 there is a pulse. So this is the form of NRZ data which is sending from the transmitter. So whenever this bit period is TB, whenever this bit period TB becomes 2 TB. So obviously when this becomes 2 TB, this portion which is now looking like this TB, now it is converting into this, that is 2 TB. So obviously this 2 TB data or the pulse is superimposing, or you can say overlapping with the next pulse, adjacent pulse in the channel. So that problem is your intersymbol interference. So in this figure, data 1, the channel input pulse width is TB here. In the second figure, the channel output pulse width is TB, but the data you can see the width of the pulse, which is initially it is TB, this time it becomes 2 TB. Similarly for data 0, if it is a negative pulse, then the data is initially it is TB, but after passing through a channel it gets spread, and the data is now has a spread of 2 TB. So obviously the data pattern which is in the continuous form from 101011, it will overlap within itself. So the data pulses overlap, and this will create your problem which is called as intersymbol interference. So to avoid intersymbol interference, there are various methods, out of which the method we are discussing here is Nyquist criteria. So we already know about Nyquist method or Nyquist frequency, which is called as sampling frequency Fs must be greater than twice of Fm. So we already discussed these things in communication engineering. So or you have already read in communication engineering that Fs sampling frequency must be greater than equivalent to twice of maximum value of the message signal frequency. So in the next figure we have drawn the same thing, that is for the input data stream we have initially the data is 101101, and the bit period or the bit duration, you can say the bit duration is TB. So for the data sequence which we are sending from the transmitter, the bit duration is TB, but in the channel, as the data gets into the channel, it gets spread, and that spreading will makes the data to be 2 TB or twice of the bit which is earlier at the transmitter. So, here the data pattern gets spreaded and the width is now becomes 2 TB. Obviously, whenever the bit becomes 2 TB, there will be overlapping. So, this is your overlapping region. So, this is overlapping, this portion is overlapping, again this is overlapping, this is overlapping. So, these all problems are called inter-symbol interference. So, between the symbols there will be interference or the overlapping due to the spreading of the data from in the channel, and this problem is called as inter-symbol interference. So, the resultant output waveform is not the similar one as the data input stream, it will be somewhat different because of the overlapping. So, whatever the data you are sending like 1010, it now becomes, now it's not difficult, it's very difficult to distinguish the data at the receiver whenever there is a overlapping between the two datas. So, next there is a tool which we can, by which we can easily measure how much is the overlapping. So, this particular tool or measurement method is called eye diagram method or eye pattern generation method. So, you can see from the figure, it is a kind of a eye shape thing which is basically like this. Okay. So, the opening of the eye is this. So, this is your opening of eye, this is the width of the eye, these are some crossings. So, here we have draw a similar type of figure or a similar type of structure for the measurement of the data which is corrupted at the receiver due to inter-symbol interference, which is called as eye pattern diagram. So, with this diagram we can easily calculate how much is the data is corrupted at the receiver. So, if the opening of the eye is not a particular or not as we want or not as high, then obviously the data is corrupted at the receiver. So, if the opening of the eye is maximum, the data is okay and the data is good, whatever we have transmitted from the transmitter, that is received at the receiver. So, this opening of the eye is basically give you an idea of how the data is transmitted from the channel and there will be inter-symbol interference or no inter-symbol interference. So, if it is blurry or if it is crossings are cutted out, then the data is corrupted and obviously whatever the data you have sended at the channel, it gets spread and there is so much of inter-symbol interference. This particular thing is known as noise margin, how much noise it can accommodate in a the data can accommodate. So, whatever the noise is adding from the channel, how much noise the data can be comfortable with, you can say. So, this is particular thing is known as noise margin. The bit duration is obviously here TB, the distortion is given with this points, these are some zero crossings. Okay. So, extensions beyond TB is obviously inter-symbol interference, which is noted down here. So, whatever the data is sended, if it is extended beyond TB, it is called as inter-symbol interference. So, with this pattern we can easily calculate how much is the data corrupted at the receiver. So, now we can see inter-symbol interference if the rectangular multi-level pulses are filtered improperly as they pass through a communication system, they will spread in time. So, and the pulses for each symbol may be smeared into adjacent time slots and cause inter-symbol interference. We have already learned in the sampling theorem, that is Fs is greater than twice of Fm, and for if it is not, Fs is less than twice of Fm, then there will be overlapping of the pulses. So, in that also we have a condition like aliasing. So, for avoiding aliasing, we can use some aliasing pre-alias filters. So, here also there is a requirement of filter. If it is not properly filtered out waveform at the channel, obviously it will give you an inter-symbol interference kind of thing. So, the input waveform here is 1,000 and individual pulse response is shown here in this figure. Receive waveform, sum of pulses response, obviously there is some spread, and that's why the received waveform is the first pulse is getting overlapped with the next pulse, which has a data which is 0. Similarly, for the pattern 1 0 triple double 1, we have a bit type of pattern like this, and whenever it is passes through the channel, it gets spreaded out, and it will be having overlapping between the two regions, between the pattern 0 1 and 1 1 also. So there is some distortion which is occurring at the received waveform, you can see from the last figure. So by this we can see that whenever the data is passed through a channel, there is some spreading and there will be a case of intersymbol interference. So how we can restrict the bandwidth and at the same time not introducing ISI, this is the main thing. So there are some techniques by which we can restrict our bandwidth also, and there is no possibility, no conditions of intersymbol interference also. So here in intersymbol interference, the first is the flat top multi-level input signal having pulse shape which is called as impulse response HT, and values of amplitude that is denoted by AK. So here W in T is a flat topped multi-level input signal, and it is given by summation of AN HT minus NTS. T minus NTS is your, all the pulses are having at a value of TS, 2TS, 3TS and 4TS and so on. So the impulse response is according to that. So initially the initial pulse has an impulse response of HT, second pulse has an impulse response of HT minus TS, third pulse has an impulse response of HT minus 2TS, 3TS and so on, having an amplitude AN. So A1 is the amplitude for the first pulse, A2 is the amplitude for the second pulse and so on. So this representation can be splitted like this also, like summation over N AN H of T multiplied by, or convolution here, that is del T minus NTS, where del T minus NTS is the impulse response. This is your shifted or delayed impulse response. So it can be written like this also, and it can be written like this also, summation over AN del T minus NTS convolution of HT, where HT is your rectangular pulse or a rect type of because the datas are in pulses, so we can represent like in a rect type of signal. So that is rect signal T by Ts, where D is equivalent to 1 upon Ts pulses per second. So what will you get at the output of the channel? So W out is equivalent to summation over N AN del T minus NTS convolution HET. So here HET is your impulse response of the channel, and that impulse response of the channel is to be convoluted with the entire signal or the entire delayed version of the input signal, and that comes out to be summation over AN HE T minus NTS. So equivalent impulse response HET having three factors here. First one is the input impulse response, your HT. Second is the transmitter impulse response, that is transmitted HTT. Then your channel impulse response HCT, and then your receiver impulse response HRT. So here there is a diagram showing the first filter, that is transmitting filter, which is having a response in the frequency domain, that is HTF, then channel filter characteristic, that is HCF, then receiver filter characteristic, that is HRF. So at the input we have W in T, which is flat top pulses, all the top of the pulses has to be initially flat, then it is transmitted through the transmitting filter, and then channel, and then receiving filter. Then we have recovered our rounded type of pulses to sampling and decoding circuits. So and after that we will use these pulses for modulation and then sending it to the for other coding circuits. So we have a series of these filters, that is HTF, HCF and HRF. As they are in cascaded form, they can be multiplied easily in the form of the frequency domain. In the time domain it has to be convolute, and in the frequency domain it has to be multiplied. So total HET, that is the equivalent impulse response, is your HT convolution HTT convolution HCT convolution HRT, or this HTT is equivalent to your HTF. This is and so on. So according to this, we can easily calculate what is the equivalent impulse response of a blocks before sending your pulses to a decoding circuit. So initially it has to be passed through these blocks and then it will be recovered as a rounded pulses. So we have equivalent impulse response, that is HET, which is HT convolution HTT convolution HCT convolution HRT. So equivalent transfer function is given by HEF, which is HF multiplied by HTF multiplied by HCF multiplied by HRF, where HF is equivalent to frequency Fourier transform of your rect signal, that is pi of T upon Ts. So this is your rect signal or the data which you have sent it from the transmitter, which is equivalent to, obviously a rect signal has a sine or sinc type of Fourier. So Ts sine pi Ts f upon pi Ts f, or you can easily write it as a sinc of pi Ts f. So here HRF is equivalent to your receiving filter impulse response or the transfer function. So HRF is the receiving filter transfer function. Basically this we have got from HRT. Okay. So after taking the Fourier transform or the Fourier inverse, we can get this transfer function. So HRF is equivalent to HEF upon HF STF multiplied by SCF. So output signal can be written like this, that is W out T is equivalent to summation over N AN HE T minus NTS. So this is your equivalent impulse response. So this is equivalent, which comprises of all these responses, the transmitted response, the channel response and the filter and the receiving filter response. So HEF has to chosen such as to minimize ISI is called equalizing filter. So this HEF is called equalizing filter, which we can use for combating our intersymbol interference. So it has to be chosen so that it will minimize your ISI. So combating ISI, there are three strategies for eliminating ISI. First, we can use a line code that is absolutely band limited. So initially if we uses a line code method, which we can restrict our pulses to a particular band or a particular width, then there will be no problem of intersymbol interference. Next would require sync pulse shape. Obviously we require a sync pulse shape. That is a good method of combating ISI. So if there is sync pulses, sync has a value maximum at a 0 and all other values are zeros at plus minus NTS. So it has some maximum value at 1 at a value of 0. So can't actually do this, but can approximate these things. So basically we can use line coding methods, and which is absolutely band limited. We can use sync pulses, but these are all approximated method. So use a line code that is 0 during adjacent sample instant. So this can be done. It's okay for pulses to overlap somewhat as long as there is no overlap at the sampling instant. So it's okay, they can overlap with each other, but they must not overlap at a particular sample instant. Can come up with pulse shape that don't overlap during adjacent sample instant. So there is a method which is called as raised Cosine-Rolloff pulse shaping method. So by this method we can avoid the thing that is the pulses is overlapping, it's okay, but they cannot overlapping at their sampling instant, at the next pulse sampling instant. So we have to see or look into this thing that the pulses can be overlapping, but it cannot be overlapping at the sampling instant. So use a filter at the receiver to undo the distortion introduced by the channel. So this type of filter is called equalizer filter, which we have seen already, that is HEF is the equalizer filter frequency response or the impulse response, by which we can if we put equalizer filter at the receiving end, then there is a much chances of we are easily combating our intersymbol interference. So next we have a method, because we have discussed so far that how we can combat our intersymbol interference. So there can be a possibility of using line code with a band limited condition, or we can use a sync pulses. So this method is Nyquist first method for 0 ISI, is basically a sync type of method. Here we are using the pulses in a form of sync shape, so that it cannot be overlap. It may overlap with each other, but that cannot be overlap at their sampling instant. So ISI can be eliminated by using an equivalent transfer function, that is HEF, such that the impulse response satisfies this condition, that is HE KTS plus tau is equivalent to C or not equivalent to 0. For that value it is 0. So at all other values of the K, it is 0, that is your equalizing filter value, and at K is equivalent to 0, if you put K is equivalent to 0, it becomes HE tau. So at HE tau it has a value of C. So which is the similar kind of thing for the sync pulse, that at sync pulse has a value maximum, that is 1, at tau is equivalent to 0, and at other values of the tau it has a 0 value. So K is an integer, Ts is the sampling period or the symbol sample period, tau is the offset in the receiver sampling clock time, C is a non-zero constant. So we can choose the sin x by x function for HET. So here W out we have already discussed that W out is equivalent to summation over n HET minus NTS, where HET is your equalizing filter at the receiver. So here HE is a sampling or SA function which is your sync function. So HET we can define here, that is sin pi FTS FST upon pi FST. So we can see from the diagram that they are overlapping with each other, but they are not overlapping at their adjacent sampling instant. So one pulse is having a sampling instant, suppose at 0 it has a value of 1. So second pulse has a value maximum at TB, and the third pulse has a maximum value at 2 TB and 3 TB and so on. So first pulse has its 0 at TB, second pulse has its 0 at 2 TB, third pulse has its 0 at 3 TB and so on. So by this way we can create a condition that the pulses can be overlapping, but they has at maximum value at some K is equivalent to 0 or K is equivalent to TB or 2 TB and 3 TB and so on, and the previous pulses has 0 value at these instants at TB, 2 TB and 3 TB and so on. So ISI occurs, but no ISI is present at the sampling instant. This is the major thing, that obviously intersymbol interference is occurring, they are overlapping with each other, the pulses are overlapping with each other, but no ISI is present at the sampling instant here. So Nyquist first method for 0 ISI, we have a filter which is HET, which we have already discussed, that is sin pi FST upon pi FST, where Fs is equivalent to 1 upon Ts. There will be no ISI and the bandwidth requirement will be minimum, that is optimum filtering, and if the transmit and receive filters are designed so that overall transfer function becomes HEF, which is 1 upon Fs, pi of F upon Fs, or we can say HET is equivalent to sin pi FST upon pi FST. So where Fs is equivalent to this. So with this figure we can have a absolute bandwidth which is equivalent to Fs by 2, which is minimum bandwidth, and the signaling rate D is equivalent to 1 upon Ts, which is equivalent to 2 TB pulses. So this figure shows the factor that with the sync pulse, if you take the inverse Fourier, you will get a rect pulse, or a rect pulse you will take a Fourier, you will get your sync pulse. So these are complementary to each other. So the next figure is showing here, that is transmitted binary PAM waveform for the data sequence 10010 using sync shaped pulses, which is raised cosine pulse shaping, that is alpha is equivalent to 0 at a transmission speed of 50,000 bits per second. So we have a figure here that 10010 is a data sequence, and for this data sequence we have a sync type of pulses, and obviously these pulses are overlapping with each other, but at the sampling instant if you see, they are not overlapping. So at the sampling instant there is no ISI, but at different locations there is obviously intersymbol interference or overlapping between the two pulses. So Nyquist first method for 0 ISI also says that sync pulses are not possible to create due to infinite time duration. So it is not possible, it's not easy to create a sync pulse as we have infinite time duration, sharp transition band in the frequency domain. So we can see from the figure that 0 crossing at non-zero integer multiples of the bit period we have, or plus minus m pi by 2 and pi by 2 we have different 0 crossings, and if you take the inverse Fourier you will get a rect type of signal. The sync pulse shape can cause significant ISI in the presence of timing errors. If the received signal is not sampled at exactly the bit instant synchronization errors, then ISI will occur. So sync pulse shape can cause obviously significant ISI in the presence of the timing errors if we have not proper timing synchronization. If the received signal is not sampled at exactly the bits instant, synchronization errors will be there, and then ISI will occur at the sampling instant also. So we seek a pulse shape that has a more gradual transition in the frequency domain. Second is more robust to timing errors. Third one, yet still satisfy Nyquist first method for 0 SI. So we require a pulse which has a more gradual transition in the frequency domain. It doesn't have a transition like it will overlapping with the next pulse, and there are some timing errors. Is more robust to timing errors. If there is some synchronization errors, then it should be robust to that, yet still satisfy Nyquist first method for 0 ISI. So with this we can see that there are lot of pulses which we can use for this method, but the sync pulse is the basic or the special kind of pulse which we can use to avoid or to combat our intersymbol interference problem, because that pulse has a unique feature or a special kind of feature that it has its maximum value at a particular point, and at all other integer points it has a value of 0. So next we have another method which is called as raised Cosine-Rolloff Nyquist filtering method. Because of the difficulties caused by the sync pulses type of pulses, consider another pulse shape which require more bandwidth, such as the raised Cosine-Rolloff Nyquist filter, but they are less affected by synchronization error. So it is less affected by timing and synchronization error. So the receiving filter or the equivalent filter having a value of HEF, and it has a value of 1 for f mod of f less than f1, and for mod of f greater than f1 and less than b, or b is the absolute bandwidth here, it has a value of 1 by 2 1 plus cos pi mod of f minus f1 upon 2 f delta. So here f delta is your bandwidth minus f naught is your central bandwidth or the 6 dB bandwidth of the filter. So f1 we can calculate here, f naught minus f delta. Here there is a term which is called as roll-off factor, which is equivalent to r is equivalent to f delta upon f naught. So here r is equivalent to f delta upon f naught, which is called as roll-off factor. So we can calculate this roll-off factor for calculating the bandwidth of the pulse. So overall pulse. So bandwidth here is rb by 2 1 plus r. So the equivalent response of the filter is HET f inverse of HEF, which is equivalent to 2 f naught sin 2 pi f naught t upon 2 pi f naught cos 2 pi f delta t upon 1 minus 4 f delta t whole square, or we can have a value this, that is roll-off factor is equivalent to r is equivalent to f delta upon f naught, or bandwidth is b is equivalent to rb by 2 1 plus r. So these two formulas are very important for calculating the raised roll-off factor and the bandwidth in the case of the raised Cosine-Rolloff Nyquist filtering. So this is the graph which is showing here the raised Cosine-Rolloff filtering method, and the 2 dB 3 dB values of here, that is 0.5, and the bandwidth is here again, that is b is equivalent to r upon 2 or rb by 2 1 plus r, or you can write it as d by 2 r 1 plus r. So roll-off factor r is equivalent to f delta upon f naught. So clock timing requirements are also relaxed in the case of the raised cosine filtering. The r is equivalent to 0 case correspond to the previous minimum bandwidth case. So b is equivalent to, in that case, f naught is equivalent f naught plus f delta. So this is the graph showing the raised cosine filtering, which we have already discussed this formula. The tails of the HET are now decreasing as much as faster than the sampling function, which we already discussed, that is the sync pulse as a function of t square. So ISI due to synchronization error is much lower in the case of the raised Cosine-Rolloff Nyquist criteria. So this is the next graph, which is showing again the same thing, that as you increase the R value, the bandwidth will also increase, or you can say as you increase the R value, the bandwidth increase and the intersymbol interference value decreases. So these are the formulas which we have already covered up, that bandwidth is equivalent to d by 2 1 plus r, or from here we can easily calculate the value of the r, or b is equivalent to r by 2 1 plus r is equivalent to 2b upon 1 plus r. So these formulas you can use in the numerical problems for calculating the Rolloff factor and the bandwidth in the case of the raised cosine method. So this Nyquist filter is called raised cosine filter is also called as Nyquist filter, and here we can calculate the value of equivalent filter, which is pi f upon 2 f naught plus yf for mod of f less than f naught, and is equivalent to 0 for all other values of the frequencies. So this is the next figure, which we can see that the raised cosine characteristics, that the filter characteristic is same as the earlier one, that is for the sampling or the sinc function. Here only the thing is that rect function is now pi f upon f naught. So thank you so much. So in the next lecture we will cover some another topic of the digital communication based on some different methods by which we can communicate over the communication channel. I think hope so this topic you can easily correlate with other topics of the digital communication, as this topic is very much important for combating intersymbol interference. Thank you so much.